Example 3. A tank containing 100 liters of a brine solution initially has 4 kilograms of salt dissolved in the solution. At time t equals 0, another brine solution flows into the tank at a rate of 2 liters per minute. This brine solution contains a concentration of 0.5 kilograms per liter of salt. At the same time, a stopcock is opened at the bottom of the tank, allowing the combined solution to flow out at a rate of 2 liters per minute, as we see here, so that the level of liquid in the tank remains constant. So we're adding 2 liters, taking out 2 liters. Find the amount of salt in the tank as a function of time, measured in minutes, and find the limiting amount of salt in the tank, assuming that the solution is well mixed at all times. Now we've got this diagram already showing all the information that we need, but let's first define some variables. First, we want to know how much salt is in the tank. So I'm going to define a function that's u of t, that is the amount of salt. The amount of salt in the tank at time t, which means that du dt, the derivative of that with respect to time, is the rate of change of the amount of salt. With this additional fact that the initial amount, okay, u of 0 equals 4. The amount of salt initially is 4 kilograms. Now we can determine what du dt is. We can determine what du dt is because that is the inflow rate minus the outflow. Inflow minus the outflow. Now we know that the amount going in is 2 liters per minute, multiplied by 1/2 kilogram of salt per liter. So this is 2 times 0.5, and the outflow rate is however much salt. So we know how much is being added in. So that's the inflow. That one's just a fixed amount over our time. But the outflow rate is a percentage of what is going out. So we know that we know what the amount is. But that divided by 100, because there's a concentration there, okay? We're talking amounts over time, so we have out of the liters, okay, times 2 because it's 2 liters per minute. So that this right here is what sets up the whole rest of the problem. So be sure you understand what's going on there. We have the amount of salt per liter, okay, because these are all salt per minute, salt per liter, things like that, okay, and we have a rate of 2 liters per minute. So let me just write out what those units are. That would be, all right, this is in kilograms, isn't it? Kilograms, yes. All right, so this is kilograms per liter, and this is 2 liters per minute. So this is kilograms per minute, whereas also this is the 2 is the liters per minute multiplied by our kilograms per liter. So that is also kilograms per minute. So we're adjusting for units really. Okay, well, if we determine what that is, then du dt is in fact 1 minus u of t and then over 50, reducing that. So let's just say this 1/50th u of t, and in fact we might just want to drop the of t. We know it's a function. Now we have this along with the fact that u of 0, the initial amount, is 4. So this is an initial value problem that we're going to solve. All right, so let's go ahead and rearrange some things. Let's see, this would be du dt equals 50 minus u over 50. See, we need to get our functions in terms of u on the left side. We don't actually have anything in terms of t, but just our u. So let's go ahead and rearrange that as we have in the past to say that that is 50 over 50 minus u is going to be a denominator. So we have du and 50 minus u. And that is dt. That'll be actually 1/50th. Just write it like this. And now we're going to take the antiderivative of both sides, which will lead us to 1/50th t on the right side plus c. And on the left side, that will be minus natural log absolute value of 50 minus u. And as in the previous problems, the absolute values will be useless. Or they will be, well, because of our constant, the signs of our constant, that could, they're not useless, but we can eliminate them that way. All right, now exponentiating. Actually, first we want to remove that negative sign. So I'm going to divide by -1, and that will make this negative 1/50th t. And I'm going to leave plus c because I don't know the sign of that. So that would be, well, we'll go ahead and do that. We'll go ahead and make this minus that. Now we've got natural log absolute value of 50 minus u equals negative 1/50th t minus c. Exponentiating. We've now got 50 minus u equals e to the negative 1/50th t minus c. And let's go ahead and write that as a constant, the constant as a coefficient. Make that c1. And we'll say c1 over here equals e to the c. All right, now solving for u, and let's bring this over here. Solving for u, that should be u of t. In fact, let's do it all the way up here. U of t equals, we've got our c1, see, subtracting 50 dividing by -1, that'll be 50 minus c1 e to the negative 1/50th t. Now let's take our initial value, u of 0, for evaluating this in here. Well, putting in 0, substituting 0 as our t value, will make this entire term 1, so this is going to be 50 minus c1. We have 4, so that would be 46. c1 equals 46, making u of t our particular solution. 50 minus 46 e to the negative 1/50 t. Now the question of what is the long-term behavior, that's the other part of this, find the limiting amount in the tank. Well, if we applied a limit, and let's make this the limit as t goes to infinity of u of t, make that the limit of 50 minus 46 e to the negative 1/50th t. We know that negative exponent, that term is going to 0, so the long-term behavior is going to be 50 pounds. That is the limiting amount. All right, for our next application problem, we have a question regarding Newton's law of cooling. So here it is stated. But I want to remind you, back in Chapter 2, 2.8 to be specific, we actually found a solution to this type of equation. And it is this. T equals T naught minus T ambient times e to the kt plus T naught. So we will solve this as an initial value, but we will end up actually with that because that is already been stated as a solution to an exponential decay problem. All right, now let's dive in and then we'll get back to some of our vocabulary. A pizza is removed from the oven after baking thoroughly, and the temperature of the oven is 350 degrees Fahrenheit. The temperature of the kitchen is 75 degrees Fahrenheit, and after 5 minutes, the temperature of the pizza is 340 degrees Fahrenheit. We would like to wait until the temperature of the pizza reaches 300 degrees before cutting and serving it. How much longer will we have to wait? All right, well, our initial temperature is 350. We're talking about the temperature, and it's going to become the ambient temperature. It's going to start at some T naught, the initial temperature, in our case 350 degrees, and it will slowly approach 75. Slowly approach 75 in a rate that is proportional to the difference between its own temperature and the ambient temperature. And if we let T of T represent the temperature, then dt of dt, capital T being our temperature, lowercase being our time, and that tells us the rate of change. That's this right here. And again, this is a solution, or the solution, general solution to this. But let's first start by writing this out as an initial value problem. We've got dt, or dt, temperature over time, equals our proportionality constant, which we don't know at this point. We will find this out, times T minus our Ts, which this actually represents the ambient temperature. So here Ta equals Ts, or I used a capital. Those two are actually synonymous. So here our ambient temperature is 300, no, it's 75. That's the 75. And we also know that T naught, or T of 0, is equal to 350. That is our initial temperature. So there's our initial value problem. So setting this up in such a way, we can write this as the integral dt divided by t minus 75 equals, I'm going to go ahead and throw the antiderivative in here, the integral of k dt. So that we have natural log, absolute value of t minus 75 equals kt plus c. Now, if we exponentiate at this point, this should begin to take shape, begin looking like that formula from 2.8. So we have no more natural log, just the absolute value of t minus 75, and I'm going to drop the absolute value because we're going to deal with that with the constant. E to the kt, I'm going to make that c1, where c1 equals e to the c. And adding 75 to both sides, we find that t is equal to 75 plus c1 e to the kt. Now let's use our value of t0 being 350 to solve for c1. Again, evaluating 0 for t, this becomes c1 75 equals 350. Subtracting 75, we have 275 equals c1. So that our particular solution is t equals 75 plus 275 e to the kt. Now, let me slide back to this equation. T equals T naught minus T ambient, which would be 350 minus 75. Hey, that's 275. E to the kt plus plus T naught, which is just the 75. So that formula does in fact work. Now we don't know the K value yet, but we were given another piece of information here. We were told that after 5 minutes, the temperature is 340, which tells us that T of 5 is 340. So let's take this equation, apply it to that. T of 5 equals 340, so this is going to be 340 equals 75 plus 275 e to the k times 5. All right, let's see, subtracting 75 from both sides, we get 265 e to the 5k. So that was minus 75. We'll go ahead and divide by 275, which reduces to 53 over 55. All right, and that is e to the 5k. We will apply the natural log.
These are the top results.
To get, let's see, 5k equals natural log 3/55, and then dividing by 5. So k is equal to natural log 3/55 divided by 5. Making our particular solution, now we have a complete picture. T equals 75 plus 275 e to the, let's go ahead and make that an approximate value. Calculator, we can approximate that as negative 0.007408. So that is e to the negative 0.007408 t. All right, now to actually answer the question, at what point will the pizza be 300 degrees Fahrenheit? When will that be 300 degrees Fahrenheit? Well, we can, now we have our complete particular solution, we can actually do some algebra. That's all we have left at this point. 300 equals 75 plus 275 e to the negative 0.007408 t. We will subtract 75 to make this 225. E to the negative 0.007408 t, dividing by 275. Subtracting 75 there. And that reduces to 9/11ths. So 9/11ths equals e to the negative 0.007408 t. Taking our natural log, as we did in the last, to find k. Natural log of 9/11ths equals negative 0.007408 t. And finally, dividing by that value of k, 7408, we get that t is approximately 27.09 minutes. Now at this point, we have waited already 5 minutes. So that means that we need to wait 22.09 more minutes.